Hello everyone, we're going to start a chapter called circular motion. When a particle moves in a plane such that its distance from a point, it could be fixed or it could be moving, remains constant. A particle is moving around a point. This point could be fixed or it could be moving such that the distance of the particle remains constant with respect to this point. Then this particle is said to have doing circular motion around this point in a plane. Alright, so the distance could remain constant and the particle may not be in the plane, but that will not be a circular motion, of course. For circular motion has to be in a plane. The particle has to go round and round and all around a point that could be fixed or moving such that the distance between that point and the particle remains constant. Then it is called a circular motion. Now that point around which the circular motion is happening is called center, and the distance between the center and the particle, which is always constant, is called radius. Okay, now as we had in case of rectilinear motion, we define quantities like position, velocity, acceleration. Similarly, we'll be going about defining the same quantities but the angular analog of those. Like for position, we'll have a quantity called angular position. Okay, now angular position, if the particle during the course of its circular motion makes an angle theta at some instant with the horizontal line, we'll be calling this as reference line, and it will mostly be always horizontal line from which we'll be always measuring the angle. So it did some circular motion and completed some part of the circle and reached here. It started from position 1 and it's reached to position 2. At position 2 it's making an angle theta. So we call the angular position to be this angle. We represent it by theta, and this is the angular position of a body. Right? Similarly, we can define a quantity like analog to velocity, which we had in case of rectilinear motion. In this case, the analog of it would be angular velocity, and this will be represented by omega. Now velocity, we know, is the rate of change of position, rate of change of displacement, rate of displacement, or rate of change of position. Now in angular terms, this definition will be the same, except for position you will have angular position. So omega is rate of change of angular position. Omega is d theta by dt, as we had v is equal to ds by dt. Change in displacement per unit time will have a change in angular displacement, or change in angular position will have angular displacement per unit time, or change in angular position per unit time. So we have a quantity called velocity. Analog to velocity, we'll have a quantity called angular velocity. Now see, all these quantities are vector quantities. As we had in case of rectilinear motion, we defined velocity and it had direction. Velocity was defined as a vector quantity. Now we'll very much like to carry forward the same idea, and we'll also attach one direction to the angular velocity so that this could also be a vector quantity, and it will help later. Now the direction of the velocity is such that you curl your right palm in the direction in which the angle around the circle is covered. Now suppose this particle is going anti-clockwise, so you will curl your right palm anti-clockwise and you'll see in which direction your thumb is pointing. In this case the thumb is pointing upward, so the angular velocity will be upward. Had it been going clockwise, then you would have curl your right palm clockwise, and in this case the thumb is pointing downward. So the angular velocity, the direction of it would have been downward. That's how you see the direction of angular velocity. Okay. Now we'll also have something called angular acceleration. Now angular acceleration would be rate of change of angular velocity, just as linear acceleration is rate of change of linear velocity. Now d omega by dt, we can also write this as d squared theta by dt, as we used to write for linear acceleration, d square s by dt square. So angular acceleration will be d square theta by dt square. Okay, so these quantities, this angular velocity, angular acceleration are radial vectors. Okay, it is in the direction, the acceleration, the angular velocity would be upward, perpendicular to the plane of the motion. Fine. Now we can also write angular acceleration as omega d omega by d theta, as we used to write linear acceleration as v dv by ds. Remember, how did we get a is equal to v dv by ds? Right in the beginning of the course when we studied differential calculus. Acceleration is dv by dt. All you have to do is divide and multiply this by ds. You club this ds and dt, that becomes v, and you are left out with dv by ds. It's a little bit of manipulation. Similar to that, you'll have angular acceleration. By the way, it is represented by alpha. You'll have omega into d omega by d theta. Okay, so this is nothing new. Till now we have learned nothing. These are the angular analogues of linear parameters. Like you will have linear, in rectilinear motion, you define the position vector of a particle. Similarly you'll be defining something called angular position, that will be represented by theta. It is the angle which the particle has covered from the reference line. Similar to velocity, you will have angular velocity. The direction of this is given by right hand thumb rule. You curl your the palm of the right hand in the direction of motion, and the thumb points in the direction of angular velocity. Similar to that, you'll have, similar to angular rectilinear acceleration, you'll have angular acceleration, which is d omega by dt. So these things you are very much familiar with. No new theory we have studied up till now. Let's start studying new things.